Structure of Sun, core. The core of the Sun extends from the center to about 2025% of the solar radius. It has a density of up to 150 grams per cc, about 150 times the density of water, and a temperature of close to 15.7 million Kelvin K. By contrast, the Sun's surface temperature is approximately 5,800 K. Recent analysis of SOHO mission data favors a faster rotation rate in the core than in the radiative zone above. Through most of the Sun's life, energy has been produced by nuclear fusion in the core region through the proton-proton chain. This process converts hydrogen into helium. Currently, only 0.8% of the energy generated in the Sun comes from another sequence of fusion reactions, called the CNO cycle. Though this proportion is expected to increase as the Sun becomes older and more luminous, the core is the only region on the Sun that produces an appreciable amount of thermal energy through fusion. 99% of the power is generated within 24% of the Sun's radius, and by 30% of the radius, fusion has stopped nearly entirely. The remainder of the Sun is heated by this energy as it is transferred outwards through many successive layers. Finally, to the solar photosphere, where it escapes into space through radiation photons, or advection massive particles. The proton-proton chain occurs around 9.21037 times each second in the core, converting about 3.71038 protons into alpha particles, helium nuclei, every second out of a total of approximately 8.91056 free protons in the Sun, or about 6.21011 kilograms per second. However, each proton on average takes around 9 billion years to fuse with another using the pp chain. Fusing for free protons hydrogen nuclide into a single alpha particle helium nucleus releases around 0.7% of the fused mass as energy, so the Sun releases energy at the mass-energy conversion rate of 4.26 million metric tons per second, which requires 600 metric megatons of hydrogen for 384.6 yacht-watts, 3.8 for 61026 W, or 9.19 to 1010 megatons of TNT per second. The large power output of the Sun is mainly due to the huge size and density of its core compared to Earth and objects on Earth, with only a fairly small amount of power being generated per cubic meter. Theoretical models of the Sun's interior indicate a maximum power density, or energy production, of approximately 276.5 watts per cubic meter at the center of the core, which, according to Karl Krashelnicki, is about the same power density inside a compost pile. The fusion rate in the core is in a self-correcting equilibrium. A slightly higher rate of fusion would cause the core to heat up more and expand slightly against the weight of the outer layers, reducing the density and hence the fusion rate and correcting the perturbation. And a slightly lower rate would cause the core to cool and shrink slightly, increasing the density and increasing the fusion rate and again reverting it to its present rate.